All right, welcome back from break. We're now going to be moving over into the open track of our reproducible research competition. All right, so funny enough, the open track turned out to be students, graduate level students, that were selected as the finalists. So it's a full student day of our finalists in this competition. So as a reminder, we're going to have the voting that takes place. We're going to see the presentation of the two finalist speakers, and then we'll show the form heading into the poster session, and you'll be able to vote on which presentation did you think was best. So first up, we have Paul Nguyen. Paul is a fourth-year PhD student studying statistics at University of Wisconsin-Madison. His research interests include Bayesian modeling and statistical learning. He enjoys rock climbing, reading, and following professional sports teams from the Bay Area. So let me get the slides going here, and then Paul will take it away.
All right, hello everyone. My name is Paul Nguyen. Today, I'll be presenting work done with my collaborators, James Maliga, Ben Lindemann, and my advisor, Samir Deshpande. In this talk, I'll be discussing the Decathlon, which essentially is a track and field super event. It consists of 10 events spread across the course of 2 days, and it tests multiple facets of athleticism, including sprinting, throwing, jumping, technique, and endurance. And so the decathlon's versatility leads some to call it the ultimate test of athletic ability. And so what we're interested in is what are the limits of human athletic performance and what do those limits look like? So a little bit more about the decathlon. The order of events of the decathlon is predetermined and it's the same every time. Day one tends to be a little bit more explosive. We begin day one with the 100-meter, move into the long jump, shot put, high jump, and then finish the day off with a 400-meter dash. And day two tends to be more technical, starting with hurdles, moving into discus, and then possibly the most technical event, the pole vault, and then the javelin, and then we finish with the grueling 1,500-meter run. And so the scoring in the decathlon, what happens is each event you earn a certain number of points, and the overall score is the sum of all of your points that you've earned so far. And the scoring of the decathlon emphasizes this versatility in that it's very, in that excelling in a single event or a single discipline isn't enough to guarantee you a top score, right? And so let's take a look at some of these top scores. Here I've plotted the last 20 years, the best decathlon performances, and I've highlighted each time the world record was last broken. So first, Roman Serbal broke it in 2001, then Ashton Eden twice in 2012 and 2015, and then Kevin Mayer set the current world record in 2018 with a score of 9,126 points. And our research suggests that these athletes are all a little bit different. Serbal, for example, is really good at jumping. Ashton, really good in the sprinting events. And Kevin Mayer, consistently good across the board. Another thing to note is the increments in which the world record was broken. So when Eaton broke the records both times, he did so in small increments, whereas Kevin Mayer, when he broke the record, he did so by about 80 points. And so we ask, is it possible to see another jump of around 80 points? I.e., is it realistic to reach 9,200 points? And if so, what does that look like? And so we have a statistical model that models each event in the decathlon individually. It's a Bayesian hierarchical model, and here are a couple of notes on it. First, we model athlete variation with an athlete event random effect. So we assume for each event that the intercepts for each athlete come from this normal distribution with an event-specific mean and event-specific standard deviation, which are drawn from a prior. We also allow for nonlinear age progression. So specifically, we use cubic polynomials for our age terms, and this kind of naturally captures the improvement and regression of athletes as they grow older. And finally, we have dependence between events. So for event E, what we do is we include terms for how the athlete did in their first event, second event, all the way on until the immediately preceding event, E-1. And so since this is a Bayesian model, we get MCMC samples of all of our parameter estimates. And with these samples from the posterior, we can simulate full decathlons. So first, let's begin with the first event, the 100-meter. We start with the posterior samples of our alphas and gammas, and there's no betas since the 100-meter is the first event. And what we do is we take one draw of alpha and gamma, we calculate the mean predicted 100-meter, and then we add random noise to get a simulated 100-meter for an athlete at a given age. We then move on to the next event. We take the long jumps, a draw of the long jumps, alpha, gamma, and then we feed in our simulated 100-meter to get a mean prediction for the long jump, and again, add random noise to get a simulated long jump for that athlete. And so we propagate this uncertainty through all 10 events, repeating this process, and then we get a full decathlon simulation for a given athlete at a given age. And if we repeat this across a grid of ages, we get age curves such as these. So here I've plotted the age curves for shot put and the 400-meter for selected athletes. These are posterior predictive intervals, and they capture uncertainty from both parameter estimation as well as uncertainty from the actual event performances. We note that they capture the actual observed shot puts and 400 meters quite well, and we see some benefits in predicting each event individually, right? So we see that the shape of the age curves are different for the shot put and the 400-meter, and we see that the predicted peaks for these events are both different, right? For the shot put, where we want the greatest distances, we see our model predicts that to happen in the later stages of an athlete's career, whereas for the 400-meter, where we want the shortest times, this happens in the early 20s. One note is that our model assumes that these age curves are identical for each athlete. This is perhaps a generous assumption, but it's one that we make because of the limited amount of data we have, right? So most decathletes don't actually complete that many decathlons. And so how we actually vary the performance by athlete are through the athlete intercepts. So recall that our model assumes that these intercepts come from a normal distribution with an event-specific mean and event-specific standard deviation, which are drawn from prior. This distribution can kind of represent the range of latent athletic skill in some event, and our athletes can be viewed as a sample from this distribution, right? And so for a given athlete, what we can do is we can take a look at their intercept and see where it falls within this normal distribution by taking their percentile, for example. And so as an example, we can take a look at Ashton Eden. We see that his 400-meter percentile is in the 95th percentile, which is great, but his 1500-meter is just slightly below median, right? And so this suggests that even the best decathletes, to get really good decathlon scores, one doesn't need to excel in all 10 events, right? Okay. So beyond looking at our favorite athletes and seeing where they stack up, we can use these profiles to kind of circle back to our original question, right? What does it take to break 9,200 points? And so to do so, we can create these profiles for these athletes, right? So take someone with Ashton Eden's profile, but not Ashton Eden himself, right? This person is great at the 100-meter, he's great at the long jump, so-so at the shot put, and so on. And what we do is we go to the distribution of 100-meter intercepts, and we take the 100th percentile intercept. We go to the distribution of long jump intercepts and take the 94th percentile, and so on. And what we can do is, or what we do is we simulate 2 decathlons for such an athlete every year from the ages 19 to 30, and we calculate the proportion of careers this athlete actually does break 9,200 points. We do note that this is perhaps an optimistic approach, as it assumes that the athletes can complete so many decathlons and they can do so across this decent chunk of time. But we do see that under this scenario, someone with Ashton Eaton's profile does break 9,200 points 6% of the time. Someone with Kevin Mayer's profile breaks 9,200 points 7% of the time, right? And we can look at, beyond looking at just the athletes that we actually see in our sample and seeing how their profiles stack up, what we can do is we can create synthetic profiles, right? So for any combination of events, we can determine what percentiles that we're interested in. And so as an example, I've made an athlete that I'm calling a day one athlete that specializes in the first 5 events. This athlete is 95th percentile in events 1 through 5 and just mediocre in the last 5 events. And we see that in our simulations, this athlete breaks 9,200 points only 2% of the time. The corresponding day 2 athlete, that's 50th percentile in the first 5 events and 95th percentile in the second 5. Unfortunately, this athlete in our simulations does not break 9,200 points, right? 2 more synthetic profiles for us to look at. The first is this unicorn athlete. They're great across the board. We'll probably never see an athlete like this, but this person is 95th percentile in all 10 events, and we see that in our simulations, if you exist, you would break 9,200 points in all scenarios. If we tune this 95 percentile to just 80th percentile, someone who's good in all 10 events, we see that now this 9,000, the probability of breaking 9,200 becomes quite small, right? So from our simulations and our analysis, we see that breaking 9,200 points is possible, but it is unlikely. And so if and when it does happen, it would be an incredible achievement. All right, some limitations. The first I touched on briefly, and it had to do with limitations in our data and how that resulted in us modeling the age curves independently. In the last slide, I talked about these profiles. We assume we chose these intercepts independently, but it would be interesting to kind of take into account correlation between those intercepts. And lastly, we kind of assume this fixed latent ability. And we do note that, of course, athletes can get better or worse due to changes in training or changes in coaching, but we leave this to future work. Thank you.
All right, thank you, Paul. Good time for one question. Question, all right. I don't run like long.
Hi. So, in your analysis, did you ever experiment with the best events that athletes should choose to be really good at? Because I know that not all events. I know that the scoring system for the individual events are not the same. So, did you ever look at which one is the one, or like which set of events is the best event for a decathlete to be excellent at?
Yeah, I'd say that we didn't specifically look at like a particular grouping to try and maximize the overall decathlon scores, but you could play around with that, kind of similar to that day 1 athlete versus day 2 athlete, right? We see that the day 1 athlete tends to score more points, but I didn't like optimize for maximizing the overall amount of points. Okay. Thank you.
All right, thank you, Paul.